65 million years ago, an unimaginable event ends the age of the dinosaurs. Today, new clues challenge the long-held ideas about an asteroid strike.
Kapow! Total cremation, if you like, reduced to ash.
We'll reveal the latest theory of exactly what happened the day the dinosaurs died, and how it could happen again. Since 1980, scientists claim that a massive extraterrestrial impact wiped out the dinosaurs. Striking the Earth with incredible force, it hurled millions of tons of debris into the atmosphere, setting off forest fires and blotting out the sun's vital rays. In the toxic aftermath, T-Rex and his counterparts found themselves trapped in a lingering nuclear-type winter. Unable to adapt, the dinosaurs never recovered and died out within decades. Many scientists agree with the basic theory that a huge asteroid killed off the dinosaurs. But the details of this cataclysmic event have remained shrouded in mystery. Now we investigate what really happened, revealing a new and dramatically different scenario that explains why the dinosaurs vanished, along with 75% of all known species on Earth.
If 75% of the individuals die, that's not an extinction at all. You recover that in a couple of generations. So 75% species extinction means 100% of the individuals in 3/4 of the species died.
Skeptics argue that if this really happened, how and why did anything survive? Professor Doug Robertson of the University of Colorado has been trying to answer this question for 10 years. He believes prairie dogs hold major clues to what scientists call the Cretaceous Tertiary extinction, or more simply, the KT event.
Well, the prairie dogs are interesting to me because they're sort of typical of the kind of mammal that survived the Cretaceous Tertiary. They're about the same size. There was nothing much larger than a squirrel. And the question, of course, is, why did things like that survive? Why?
Why would turtles, lizards, and crocodiles survive, but not dinosaurs? What's the common link that unites the creatures that made it through the extinction event?
My original idea was that the survivors looked an awful lot like hibernators. Mammals, turtles, lizards, they're all things that hibernate. And the problem with that idea was birds. Birds survived, and birds don't hibernate.
So hibernation seemed plausible, but was wrong. Clearly, another survival mechanism was involved. To find out what, scientists need to know what hit the Earth and what effect it really had. Bill Bottke specializes in the movements of planetary bodies. He employs complex mathematics to track the trajectories and orbits of planets over millions of years. For a decade, Bottke's been searching for the culprit that struck Earth 65 million years ago. A chief suspect is a comet. Comets originate in the Oort cloud some 5 trillion miles away that surrounds our entire solar system. The theory is that a killer comet traveling at about 100,000 miles per hour hurtled into the inner solar system and hit Earth.
Our star is in a galaxy where there's lots and lots of stars, and so from time to time we pass close to other stars. And when we do, the gravitational force of those stars can jostle the Oort cloud and actually, in some cases, change your orbit and send many comets in towards the inner solar system.
The assumption that a comet from the distant Oort cloud wiped out the dinosaurs has become widely accepted.
There are many large comets flying around, so when people sort of calculate the probabilities, it didn't seem incredibly unlikely that a very large comet could have slammed into the Earth in the past.
But in the early 1990s, when Bill Bottke is studying planetary science at the University of Arizona, an event occurs that leads him to challenge the comet theory. On October 29, 1991, after 2 years traveling through space toward Jupiter, the Galileo probe reaches the asteroid belt. In this vast ring of rocks between Mars and Jupiter, Galileo performs several asteroid flybys. The asteroid Gaspra is its first target, where it takes a series of photos, the first ever taken from a nearby spacecraft. The pictures show Gaspra to be about 12 miles long and 7 miles wide. They also reveal a scientific puzzle.
It's covered by craters. It's covered by a soil, which they call regolith, which is made from micrometeorite impacts. It's a whole new world.
When big asteroids collide, they create many micrometeors. These meteors shower their neighbors, leaving tiny impact craters. Major collisions are highly unusual because the asteroid belt is not the crowded place we usually imagine.
When people think of the asteroid belt, they often think of movies. And in the movies, the asteroid belts are always amazingly dense places. You know, they think of the movie The Empire Strikes Back with the Millennium Falcon careening around asteroids trying to avoid being demolished. But in general, at least for our asteroid belt, things aren't that way.
This is what makes Gaspra so striking. Its cratered surface shows signs of a rare asteroid collision and offers the first clues to why the dinosaurs suddenly vanished. Gaspra's close neighbor is an asteroid called Baptistina. Baptistina behaves like a single asteroid, but in fact, it's a family or cluster, the largest about 25 miles in diameter. Unlike Gaspra, none of them has microcraters. Bottke's conclusion is simple. Baptistina was once a single 100-mile diameter asteroid. But in the distant past, a rare event occurred. It was struck by another asteroid and shattered into millions of fragments. The tiniest of these fragments pepper nearby Gaspra, creating its distinctive microcraters. What remains unclear is what happens to the bigger pieces. Bottke wonders if one of them strikes the Earth and wipes out the dinosaurs. His theory is good, but needs more information about how asteroid clusters behave. At NASA's Ames facility in California, scientists simulate the behavior of asteroids when there's a collision. Pete Schultz, a leading impact specialist, conducts the experiment using a high-density clay model of Baptistina. A metal ball bearing serves as the impact asteroid.
So what we're going to do is to suspend this model of an asteroid and see what happens when another smaller asteroid comes barreling through this opening. Okay, we're out of the gun. Lock and load.
The experiment aims to determine how many fragments result from an asteroid collision and what happens to them.
Oh, jeez. Oh, there's nothing left. Oh, kapow! It's being smashed to smithereens. There's just nothing left. So let's see what we have. This is with the really high-speed camera. Okay, one frame. Oh, jeez! This is the moment an asteroid ran into another one. One more frame. One more. And now the whole thing is breaking apart. You can see the pieces. Keep going.
The experiment takes place in a vacuum chamber. Amazingly, 3 of the largest pieces stay close together. This is crucial to understanding how asteroid families like Baptistina form.
Okay, let's see what we did. Oh, look at this. There are pieces everywhere. We bashed this completely apart. There's a piece over here. We bring these things back together. So imagine this were in space. Gravity would be pulling some of these fragments back together, and they would eventually form a new asteroid, but they'd be made out of the fragments of the old one.
This demonstration proves that the physics of the asteroid belt defy common sense. Logic dictates that the exploding fragments should push apart. But in fact, only the smallest fragments are hurled into space. Small fragments like these showered Gaspra. The bigger pieces of Baptistina eventually drift back together, forming a family. And millions of years in the future, this family will solidify back into a single asteroid. By calculating the size of the original Baptistina before it was hit, Botke realizes several of the bigger fragments are missing. Where did they go? Botke has a hunch. Maybe the other fragments were hurled toward the inner solar system and the Earth.
Well, the Earth lives in the middle of a cosmic shooting gallery with asteroids and comets flying around all the time. But there aren't many big ones. So in general, when they fly around, they tend to miss, unless you're going to spend a very long time waiting. However, if you increase the population of big ones, then your odds are that the Earth is going to get hit.
Botke wonders if the breakup of Baptistina increases the number of big asteroids in the inner solar system. If he's right, he will almost single-handedly revolutionize our understanding of the dinosaur extinction and how similar extinctions might happen again in our future. But the next step in his investigation is the toughest. He needs to know when the breakup of Baptistina happened. When Botke began his research, the complex mathematical equations that could work this out did not yet exist. But possible physical evidence did. It seems the Baptistina breakup sent more than one asteroid hurling in the direction of Earth. And human explorers had already found the area where the second asteroid struck. Hard physical evidence for what abruptly ended the age of the dinosaurs is here at West Bijou, Colorado, near Denver. It's called the Iridium Layer. It was first uncovered by father and son team Luis and Walter Alvarez in 1980, a physicist and a geologist. Scientists have since found iridium all over the world, and deposits are all 65 million years old. Iridium is normally found only in deep space on comets and asteroids. The Alvarez team argued that only an asteroid or comet impact could explain how a thin layer of iridium had covered the entire planet at the same time the dinosaurs vanished. Their theory turned the scientific world upside down.
It was something dropping out of the sky, and it wasn't a natural part of geology, but it is a natural part of geology.
After finding the iridium layer, the search began to find the crater. It took 10 years. Eventually, it is discovered off Mexico's Yucatan Peninsula. The Chicxulub crater is about 180 miles across and can only be seen using gravity maps provided by satellites. But a fundamental mystery remains. The iridium layer can't explain what killed the dinosaurs. Scientists first thought the vast amounts of dust and debris called ejecta released into the atmosphere by the impact were the cause of the extinction.
The first thing that came to mind was the worldwide darkness, the nuclear winter sort of effect from dust in the atmosphere.
Nuclear winter is a phenomenon scientists predict would follow an atomic war. Dust would blot out the sun, causing temperatures to plummet, destroying the food chain. Over the course of years, mass extinctions would inevitably follow. But some were skeptical that less than an inch of dust, even on a global scale, could do this.
We don't believe that impact produced that much dust. And so we were very puzzled about what it is that could possibly have been about an impact that caused a global extinction.
But at the KT boundary, there is a clue. Sampling reveals unusual quantities of soot. Quantities sufficient to suggest fire on a size and scale perhaps never seen before on our planet. Unraveling how an asteroid triggered global wildfires is at the heart of the new picture of how the dinosaurs really died out.
What could have caused fires to occur all at the same time, all over the world?
The answer lies in what happens to the ejecta after it's thrown into the atmosphere.
We realized that the ejecta, in the process of getting to distant sites around the Earth, had to be moving pretty fast, almost 8 kilometers per second. And that ejecta moving that fast was carrying a lot of kinetic energy. That energy had to go someplace. And where it must have gone is into the upper atmosphere of the Earth. And that, heating the upper atmosphere, would have caused thermal radiation, and aha, that's what must have caused the fires.
The only way for Meloche to prove it, even in theory, was to do the longhand calculations.
The energy per unit area was brought in by this amount of...
He needed to calculate how showering the globe in an 1/8 of an inch layer of particles, traveling at high velocity, could generate enough energy to superheat the entire atmosphere.
And it comes out to be a total of about 10 to the 8th joules per square meter. That's a lot of energy.
According to his calculations, the amount of energy unleashed by the impact ejecta falling back to Earth was staggering.
That's equal to 60 times the heat of the sun coming down vertically at noonday. That's a tremendous amount of energy and would light global wildfires and probably kill all the animals on the ground.
The sums added up, but Meloche had no physical evidence. Then, in 1994, the Hubble Space Telescope spectacularly confirms Meloche's theory. Fragments of comet Shoemaker-Levy 9 plunge into the atmosphere of Jupiter. The impacts throw out vast clouds of ejecta that cause so much invisible thermal radiation that it's felt as far away as Earth.
Shoemaker-Levy 9 created a pulse of thermal radiation that actually burned out an infrared detector in Australia. It was that intense that we could burn out detectors across the solar system. Now, those Shoemaker-Levy 9 impactors were tiny compared to the KT impactor. Those were fragments of comet probably 300 meters across. The KT impactor was 15 kilometers across.
Back at NASA Ames, Pete Schultz tests the global firestorm hypothesis with high-speed photography expert Jean-Pierre Wiens. This time, he's shooting a small steel projectile, the asteroid, into a 3-foot diameter of fine particles he has prepared to represent the surface of the Earth.
Oh, God! We actually get to see the fireball coming through the atmosphere before it's actually hit the surface. It's going to hit right here. Okay, let's go to the next. Kapow, that hits. What we're now looking at is this hot plasma expanding at the temperature of the sun. And then as this gets bigger and bigger, as the crater begins to grow, there's more and more ejecta that you can see. That is debris being tossed out. That's going above the atmosphere and will return that back through, creating another fireball, thousands and billions of fireballs as all that debris comes rushing back through the atmosphere at 5 miles per second. It's a terrifying thought, but here we have just a small scale example of it.
Schultz's test will help prove what happened to the dinosaurs. The experimental impact first creates plasma. During a real asteroid collision, this would have instantaneously annihilated almost everything within 1,000 miles of the blast zone. The key is what happens after. Even this tiny impact has produced a rain of particles that fills the chamber. If this were the KT impact, these particles would reach the edge of the atmosphere, falling back to Earth as superheated debris. How did any living creature survive this firestorm? And what caused the asteroid to strike Earth with such devastating force? On December 7, 1972, Apollo 17, the last manned mission to the moon, blasts off. The astronauts' mission is to take rock samples from near the site of the suspected asteroid impact. Called Tycho, the crater is more than 50 miles in diameter and nearly 3 miles deep. Nearly 40 years later, what the astronauts find provides a vital clue about the origins of the dinosaurs' killer asteroid. Bill Bottke's investigation of the breakup of the asteroid Baptistina has led him to propose that one of its fragments hit the Earth 65 million years ago. Tycho can help prove this.
They took the materials back to the Earth, they measured how long they'd been exposed in space to cosmic rays, and they got an age of about 110 million years. So Tycho formed, presumably, right in the middle of this asteroid shower from Baptistina.
But the asteroid that created Tycho did so 45 million years before the extinction of the dinosaurs. To prove that both these asteroids were once part of Baptistina, Bottke needed to know when Baptistina broke up. And this took an amazing piece of science only rediscovered in the late 1990s.
What we in this community have turned to is a very strange and unusual effect, which people often refer to now as the Yarkowski effect.
Iwan Yarkowski was a 19th century Polish civil engineer who spent his spare time probing complex mathematical mysteries. One of them was what causes some asteroids and asteroid families to drift apart and change orbit, when the gravity of the asteroid belt normally makes them drift back together again. We can demonstrate what the Yarkowski effect is and how it works with the help of Bill Bottke's daughters and their friends. Imagine a small asteroid, the single girl, striking Baptistina, represented by the group of girls. As the asteroids collide and Baptistina splits into a number of smaller asteroids, a cluster, it continues to orbit around the Sun and inner planets, represented by the balls. Even though the asteroid fragments, the girls, all stay within the asteroid belt, the red hockey circle, over time, some of them drift far apart. Yarkowski realized that how far the asteroids drift apart is dependent on their ages and sizes. But his greatest discovery is that although gravity usually forces asteroid fragments back together, sometimes a different force pushes them apart. This force is solar radiation. Over millions of years, the heat of the sun can create a tiny amount of thrust, driving some asteroids apart. Knowing this, scientists can work backward and calculate when the breakup occurred.
So what we can do is when one looks at an asteroid family and you look at the spread of the fragments, the small guys versus the big guys, if you understand how the Yarkowski effect works on those asteroids, you can use how far they've traveled from the impact site like a clock to tell you when that breakup took place.
Calculating back over tens of millions of years, Bottke now has a precise date for the Baptistina breakup, 160 million years ago, long before the Tycho impact on the Moon and the dinosaur extinction on Earth. It could, therefore, have caused both. But if the Yarkowski effect allows us to date asteroid clusters and determine how they sometimes separate, it takes another equally complex phenomenon to explain how some of these fragments end up on a collision course with the Earth and Moon. This powerful process is orbital resonance. It occurs when a planet, the blue dot, and an asteroid, the red dot, keep meeting at exactly the same point as they orbit the Sun. This causes a tiny gravitational kick on the asteroid every time they meet.
Over lots and lots and lots of orbits, over hundreds of thousands of years to millions of years, all those little gravitational kicks build up, and they can actually change the orbit of the asteroid.
Resonance explains how the normal circular orbit of an asteroid becomes wildly elliptical. Once this happens, it can end up on a collision course with the Earth. According to Bottke, it took the combination of the Yarkowski effect and resonance nearly 100 million years to send a fragment of Baptistina hurtling into the Earth. But the smoking gun that might prove the theory would be hard physical evidence. Asteroids can be made of a variety of minerals. Recent analysis of the 65-million-year-old KT boundary has pinpointed exactly what the asteroid was made of.
We believe that the impactor was what is called a carbonaceous chondrite. That's one of the kinds of asteroid materials that exist in the solar system. It was unclear at first just what the impactor might have been. Some people thought it might have been a comet, in fact, but it's now known to be this stony, carbon-bearing material which is floating around out there in our solar system, and occasionally a chunk comes in and hits the Earth.
If the Baptistina cluster is a match for the asteroid that struck Earth 65 million years ago, it would reinforce Botke's theory. For that to happen, Baptistina needs to be a carbonaceous chondrite. Today's telescopes use advanced techniques to measure precisely the amount of light that celestial bodies reflect from the sun. The amount of light reflected by the Baptistina cluster is consistent with a particular type of asteroid, carbonaceous chondrite. A perfect match. This discovery has helped Botke's pioneering theory gain international recognition. Almost certainly, we now know 160 million years ago, an asteroid called Baptistina breaks up, struck in a rare collision with another asteroid. Almost immediately, the shattered Baptistina showers its neighbor, Gaspra, in ejecta. But several much larger fragments, miles across, are set on a course that will eventually send them hurtling into the inner solar system. "50 million years later, our moon is struck by a 3-mile diameter asteroid, creating the vast crater called Tycho. Another 45 million years later, an even bigger asteroid strikes our Earth, creating the massive Chicxulub crater off Mexico's Yucatan Peninsula, bringing an end to 3/4 of all species on Earth.
The impact of an asteroid the size of the Chicxulub impact would be a catastrophe beyond imagining. It's really the worst thing that could happen to our planet. If humans had been here 65 million years ago, they would have gone extinct, just like the dinosaurs.
But scientists have long struggled to understand why some creatures survived and some did not. Why did the dinosaurs die off, but not lizards or other reptiles? How did mammals become inheritors of the Earth? For years, Doug Robertson has been tirelessly cataloging all the known survivors of this devastating impact, examining the mammals, birds, insects, and fish, trying to uncover the missing link that allowed them to survive. Robertson first proposed it was the ability to hibernate through the long months of darkness and toxic nuclear winter. But birds survived, and they don't hibernate, so something else must have united the creatures that made it through. Robertson's search eventually leads to a scientific paper that proposed a revolutionary new theory about what happens when an asteroid impacts on the Earth.
It was this article in the journal Nature that changed my thinking about what had happened, what had caused the great mass extinction at the end of the Cretaceous. The time scale suddenly shifted from months to hours.
Previously, scientists were convinced it took years to wipe out the dinosaurs. At last, Robertson has discovered a theory that states it could have happened in a flash.
The upper atmosphere would start turning a little bit red. Maybe a few meteors would appear, even in the daylight, very, very bright. But the ejecta raining into the atmosphere would start heating the upper atmosphere. The sky, normally blue, would start turning red. And as it turned red, you'd begin to feel the heat beating down from the sky, as if there was a giant heating element in the sky, just turning it on. As the minutes passed, it would get hotter and hotter. In the forest, leaves would begin to shrivel up, begin to smoke and curl. The heat would get more and more intense.
Armed with this knowledge, Robertson realizes the Earth literally caught fire.
We're talking blast furnace temperatures. We're talking temperatures that would incinerate, not just kill, but incinerate, completely destroy bodies, logs. Any organic material would be just completely gone. Total cremation, if you like. Reduced to ash.
The kill mechanism was very sudden, and this provides the critical breakthrough Doug Robertson needs to explain why some birds survived the impact.
You don't need to be hibernating. You can just be sheltered somehow underground. And there are birds that burrow. There are a dozen-odd species that nest in burrows.
The common link for the survivors is simple. They had to get underground or underwater. The firestorm would burn any species unable to take shelter in minutes. That's why prairie dogs are a perfect example of the sort of creature that survived.
Here we have a prairie dog hole. This will go down 10 or 15 feet. And this would be typical of the kind of burrow that would have protected something against the firestorms at the end of the Cretaceous. And if you ask what is it that would have had a population underground or in the water at the time of the impact, the answer is mammals, lizards, turtles, frogs, fish, even birds. Some of them nest in burrows. And that's an exact match for what made it through.
If the global firestorm theory is correct, we can now recreate the full sequence of events that led to the end of the dinosaurs. 160 million years ago, Baptistina collides with another asteroid. Millions of years later, a giant fragment from this impact is caught in an orbital resonance, sending it on a long journey toward Earth. Eventually, this gigantic asteroid fragment strikes the coast of Mexico, creating the vast Chicxulub crater. The impact sends millions of tons of particles into the atmosphere at high speed, superheating the planet. Any creature able to retreats from the growing heat. But too big to escape, T-Rex and the other dinosaurs are caught in a global firestorm. Their extinction measured not in years or decades, but hours and minutes. The big question confronting humanity is, if an impact of the same size strikes us again, would we survive?
I get up early, I get my kids ready for school. I do the typical house stuff, laundry, clean.
Today, all over the world, telescopes are scanning the skies, searching for rogue asteroids that might strike the Earth. The chances of us being hit by anything big are remote, but not zero.
The near-Earth asteroids, those with orbits that cross the orbit of Earth, those that are capable of hitting the Earth, are just out there. They're in space. We live in a shooting gallery.
In response to this threat, scientists have proposed a number of potential asteroid defense systems. Many scientists completely dismiss one type of asteroid defense, popularized by Hollywood films.
After you detonate a nuclear weapon near an asteroid, it's radioactive, and it's in small pieces that are still heading toward the Earth. And it's just a question of whether you want one single chunk of an asteroid to hit the atmosphere or a large number of chunks that are now radioactive. Probably a bad idea.
There are several viable proposals for defending the planet. Meloche has proposed his own unorthodox method for deflecting asteroids: mirrors.
The idea we came up with is simply to collect sunlight with a big mirror, a solar collector, something that would gather the sunlight, focus it down on the asteroid so intensely that it would heat the surface of the asteroid up. Even rock under those conditions will vaporize, jet off the surface, and just like a little solar-powered rocket, over time, that gentle push would push the asteroid out of a collision course with the Earth.
But what might happen if an asteroid the size of the one that wiped out the dinosaurs hit us today?
I would hope that some people could survive, but for most of us, it would be the end of the world.
Imagine that deep within the asteroid belt, a collision just like the one that created the Baptistina cluster has already happened. And that right now, after tens of millions of years hurtling through space, it's just a few days away from a collision with Earth. The 8-mile-wide asteroid has gone unnoticed until now. It seems that history is about to repeat itself. Frantic preparations begin, but it's too late to avert the disaster, and the world's governments can't agree on what to do. Experts like Doug Robertson and Jay Meloche try desperately to advise others on how to survive the disaster.
You need to be prepared to get underground, get away from the thermal radiation, the heat, the debris falling from the atmosphere, and take about a year's worth of supplies with you.
You might want some sort of rainwater catchment system. You might want to locate a spring, but you have to worry about your long-term food supply.
With the world in deep shock, many people carry on as normal. Others fall prey to mass hysteria. As news media try to predict what will happen next, all over the world, millions of people are on the move trying to escape the blast zone. Thousands of miles away, the most reckless sightseers are even preparing to film the event. They've been told the impact will cause the greatest sunset in 65 million years. The final countdown begins. 5, 4, 3, 2, 1. The asteroid strikes. The impact instantly incinerates everything within 1,000 miles. The debris swallows up whole towns. Meanwhile, billions of particles of shattered asteroid are sent hurtling high into the atmosphere. As they rain back down to Earth, they generate thermal radiation that starts to spread all over the globe. For sightseers, temperatures begin to soar. Soon it's unbearably hot. Then, the world catches fire. For most of the human race, there is no place to hide. Within hours, 75% of all species on Earth are extinct. Every member of humanity without shelter has been incinerated. The survivors eventually emerge from the subways, cellars, and bunkers they were lucky enough to hide in. Among them, Jay Malash and Doug Robertson.
This is the National Geographic Channel.